Hello everyone, my name is Bhaskaran and this is going to be a quick video about how to find resistance looking into a node of any analog circuit. So first of all, we're going to start off with the procedure to find the small signal resistance looking into a node. So we'll discuss the steps and then we will do about 3 or 4 examples to sort of apply those steps and see how we find the small signal resistance looking into a node. And then finally, a little bit of bonus content, but we will discuss practical use of negative resistance in LCD seals. So let's get started. Um, by the way, from one of the videos from before about the small signal models, I discussed the NMOS small signal model, which is shown over here. One thing I wanted to point out is that PMOS small signal model also looks very much similar to the NMOS. So in the PMOS, you would have something like this. So GMVGS, and you would have GDS, and the IDN would be this direction, and then the gate noise would be something like this. And so, yeah, the PMOS small signal model is very much similar to the NMOS small signal model. Same idea for all of the analysis, okay? All right, so let's look at the steps to find the small signal resistance looking into a node. First, step one is that we short any DC voltages in our schematic, any DC voltage sources. Step number two is we open any current sources. Step number three is we draw a small signal model. And then step four is that whatever node that we're trying to find the resistance looking into, we introduce a hypothetical test voltage source, and we look at the current, the test current that is going into the node. So let me explain this fourth point a little bit more. So imagine if this is the node, and we are trying to look into this node and finding the resistance. Let's call it our route, okay? So then what point number 4 or step number 4 is saying is that at that node, we attach or we introduce a test voltage source. This is a small signal source, by the way, and we look at the small signal current uh, at this node, all right? And so what this means is the R out would be simply V test over I test, all right? So that's basically how we find resistance looking into any node of a circuit. So let's do some examples. Resistance looking into the source of the MOSFET. So that's the first example, and we are looking at this node here. We're trying to find out the resistance R out. Okay, so I have already drawn the small signal model on the right. Now, step one was to short any DC voltage sources. In this case, that's the bias voltage here. And so the gate will be grounded. Similarly, this is also a voltage source, and the drain can be grounded, okay? And the source is what we are trying to look into. So at the source, we can introduce the small signal voltage source, we test, and we look at the current I test, okay? So let's write down some equations, KCL at node VS. So we can write I test is equals to GM, oh, sorry. I test plus GMVGS is equals to V test GDS. So then we can rewrite this equation saying I test equals to minus GMVGS plus V test GDS. And then I test equals to minus GM. And then VG is grounded, and then source is V test. Voltage at source is V test, and then plus V test GDS. So in other words, I can write down that V test over I test would be something, oh, sorry, I missed the sign here. So that should be, oh yeah, no, that's right, that's right. That's the negative sign, and we can write 1 over GM plus GDS. So that's the V test over I test, and that is equal to R out. Okay, so resistance looking into the source of the MOSFET is, well, I can also write this roughly equal. If assuming that GM is much greater than GDS, I can write that this term is roughly equivalent to 1 over GM. Okay. And by the way, this used to be true for older processes, not so much for the newer processes. So take this approximation with a grain of salt. But essentially, resistance looking into the source of a MOSFET is 1 over GM. Now, one thing from the previous videos is GM is, if I draw the ID VGS curve of a transistor, so VGS curve, it would look something like this, right? And we previously talked about it, and we said that, you know, GM is basically the slope of this curve. All right. So GM is usually a large number, which means that 1 over GM is a small number. And so this is a small resistance. So resistance looking into the source of a MOSFET is a small number. Okay. So I want you to sort of just hang on to that thought for a while. Okay, let's move on to the next example, which is resistance looking into the drain of the MOSFET. So looking into this node. So that's the R out this time. And again, same thing, we short the voltage supplies. So this is grounded, and then at the drain, this is our node, and we're going to introduce a small signal test. Let's call it VO, test voltage source, and the current going in is IO. So I've called it V naught and I naught for the test voltage and current source. So you can call it whatever. You can call it V test and I test, or V naught and I naught. It doesn't matter. But the R out in this case is going to be V naught over I naught. Okay. So if we write KCL at VD, which is this node, then KCL at VD is going to be this equation over here. Just tidy it up a little bit. And you'll find out that R out is equal to 1 over GDS. Now, that's the resistance looking into the drain of the MOSFET. So let's do this thing. In the previous videos, we talked about GDS, and we said that if we draw a curve of the MOSFET VDS versus VDS versus ID, then we have something like this, right? And GDS is basically the slope over here. And this slope is usually small. So GDS is, if GDS is a small number, then 1 over GDS is high. And so the resistance looking into the drain of the MOSFET is usually a high resistance, okay? So I want you to remember that as well. Now, going on to the third example, resistance looking into any terminal of a diode connected MOSFET. So now we have a diode connected MOSFET, and this is the R out. And I have drawn the small signal model and basically done all the work. And if you do KCL at the node VD, you can find out that R out is roughly equal to 1 over GM. It's a very simple derivation. And again, here we looked at the drain of a diode connected MOSFET. Over here, we look at the source of a diode connected MOSFET. And we will find out that R out is still 1 over GM. So looking into the drain of a diode connected, it's 1 over GM. Looking into the source of a diode connected, it's still 1 over GM. So in a way, you can say resistance looking into any node of a diode connected MOSFET is 1 over GM, which is, again, a small resistance. So let's look at the summary. Again, resistance looking into the source of a MOSFET is 1 over GM, which means low resistance looking into this node. Looking into the drain is a high resistance. And for for a diode connected transistor looking into any terminal, gate, drain, or source, it's going to be a low resistance, okay? And you can just finish the values over here of the resistance. All right, so far we have only looked at single-ended circuits, all right? we can also find, using the same method, using the same procedure, we can also find the resistance looking into a differential node. So let's look at an example for that. So here I have, I have a circuit. Okay, so this is, I want to find the resistance looking into this differential node. Okay, so let's call it Rn. And for this example, let's assume lambda is 0. All right. So same procedure. We introduce a test voltage source, in this case VA, let's call it VA. And at this leg of the differential node, we call it VB. And there's some test current going in, let's call it I out, I naught. And the same current that is going in is going to come out at the other node. So that's also I naught, but it's the opposite direction. Okay. And so Rn, which is resistance looking into this differential node, would be VA minus VB divided by I naught. All right. So let's come up with an expression for that. I have drawn the small signal model, and if you do KCL at node VA, you'll find this equation. And if you do KCL at node VB, you'll find this other equation, and you can write both of these equations until you get the final form, which is this equation here, equation 1, and you can find the other, which is equation 2. So this is, equation 1 is VB over I naught, and equation 2 is VA over I naught. So going back, we said that the input resistance into the differential node is defined as VA minus VB divided by I naught. So we can try subtracting equation 1 from equation 2, which is VA over I naught minus VB over I naught, and that will give us, let's look at this, minus 1 over GM2 minus 1 over GM1. And if GM1, if we assume that GM1 is equals to GM2, then we can simplify and write the input, the input resistance, the input differential resistance would be minus 2 over GM. Okay, so that's how you find resistance looking into a differential node. All right, so that's pretty much it for this video. I just wanted to show you how to find resistance looking into any node of a circuit. Now, what I'm about to say now is going to be more of a bonus content. It's not really part of the video. It's just basically the circuit that I've shown you here, right? We found out that the differential resistance, looking into this node is minus 2 over GM, which is the result we had here. Now, what's intriguing is that the input differential resistance is minus 2 over GM. So it's a negative resistance, right? And I remember when I was in my analog classes, and the first time I heard about negative resistance, I was very curious. I was like, is this negative resistance? How do you build a negative resistance? Is this even real? Is this practical, or is it just a hypothetical concept? And turns out it's pretty much real, right? Like, look, there's this circuit that has a negative resistance. So you can generate negative resistances, and it turns out that you can use them to your advantage. So let's look at an example of negative resistance being used in an analog circuit. So here, consider that there's an LC tank, right? So this is back to like high school physics, where when the capacitor de-energizes, the inductor will energize, and it will store energy. And then when the inductor de-energizes, the capacitor will energize, and so the energy will keep flowing between like the capacitor and the inductor back and forth, and that gives us an oscillation from an LC tank. All right. Now, in practice, what we find is that if we have an LC tank in real life, the oscillations would start, but then they would dampen out. It would die out. The oscillations would die out. And the reason for that is this L and C in real life is not perfect. In in reality, what we will find is that there's this parasitic resistance, which appears in parallel to the LC tank. And this is not an intentional resistance. This is not a resistance that is, sorry, this is not a resistance that is, part of the schematic. This is a resistance that's just there when we, have an LC tank, when we realize an LC tank. And so the reason for the oscillations to damp out is that every oscillation cycle, some current flows through this parasitic resistance, and the energy is lost in terms of due to heat when it passes through this when current passes through this resistor, right? And so when you lose energy on through this parasitic resistance on every oscillation cycle, eventually the oscillations will die out. So that's kind of like a showstopper if you want to build an oscillator that should keep oscillating. If you want to build an oscillator, you want to find out a way where you can sort of cancel out this parasitic resistance. So let's hold on to that idea and see how we can cancel out this parasitic resistance. So here's an idea. What if the resistance in parallel to the LC tank was infinite, right? If this branch had infinite resistance, right? If this branch here, which appears parallel to the LC tank, this resistance was infinite, then no current would flow through it, right? Which means no energy would be lost in the parasitic resistance. And so, which means that the oscillations could continue forever, or in other words, oscillations could be sustained. And that is something that we want. So let's look at a way we can do this. So we have this part that we know of, but then let's imagine that we have a resistance over here called RDEF, and that's a negative resistance. So let's see the parallel combination of R parallel and this negative resistance called RDEF. And that would look, the parallel combination of, or the equivalent resistance of this parallel combination will look something like this. Now, if we can ensure somehow that this negative resistance is equal to the negative of R parasitic, then what we would find out is that the equivalent resistance, like resistance looking into this node, would be infinite. So let's recall this differential circuit that we talked about earlier. We talked about this circuit, which creates a negative resistance, and the value is -2/Gm. All right. So in other words, if this resistance is between nodes A and B, then equivalent equivalent representation of this differential resistance would be RDEF between nodes A and B, and the value of it would be -2/Gm. All right. Now, building on this concept, let's say that we have this RDEF, which is -2/Gm, and we can design the Gm of this circuit such that the RDEF is equal to the negative of R parasitic, right? And if we can do that, then that means the equivalent resistance that appears in parallel to the LC tank would be infinite. And which means that if this equivalent resistance is infinite, then no energy is going to be lost during oscillations, which means the oscillations could be sustained forever, right? And that is basically the working principle of a typical cross-coupled NMOS LC VCO. So this is a circuit, and this is the circuit, and we have R parasitic. Again, this is not an intentional resistor. This is something that just appears because our L and C are not perfect. And so this circuit over here is all it's doing is it's generating a negative resistance that negates the parasitic, the R parasitic in pink here. And if it negates it properly, then the equivalent resistance of this combination here would be infinite. And so no energy would be lost in this combination. And so this topology is called NMOS, cross-coupled NMOS VCO or LC-VCO. Now, it's like so far what I've discussed is pretty much an oscillator, not a variable oscillator. But you can basically have a capacitor. If it varies, then this circuit would basically become a VCO, right? And you can vary the capacitance to vary the frequency of this oscillator. So yeah, that's basically one of the ways you can build an on-chip oscillator. And the concept of negative resistance is important in making this oscillator work. And so I just wanted to show you guys an example of how we can use negative resistance as an analog designer to our advantage, and basically fabricate an oscillator that works in practice, and the oscillations can be sustained just like it would in an ideal oscillator. Now, just one closing note. This is the working principle. This is just the working principle of an LC-VCO, a cross-coupled NMOS LC-VCO. But in reality, when you design, one of my projects was to design a cross-coupled NMOS LC-VCO, and when you get to designing, there's much more theory that you want to work on or understand. There's a lot of theory about phase noise of VCOs, and power consumption, and all these different trade-offs for a VCO that we need to consider. But this is basically the working principle, and I just want to show you how negative resistance can make it possible for us designers to have an oscillator on chip. So yeah, that is pretty much it for this video, and I hope to see you in the next one. See you. Bye-bye.